students, and welcome back to Study Room. So as I told you in the last class that we are going to now learn about the electric motor. So you must have heard the word motor, right? You must have heard your mother or father saying switch on the motor or switch off the motor or the motor isn't working. So what exactly is the motor and how it works, that we are going to see today. Okay, let's go. Okay, so first we're going to see what exactly is an electric motor. So an electric motor is a rotating device. Okay, this you have to keep in mind that there is something, we don't know what yet, we will learn about that, but there is something or some piece in the motor which rotates, and this is the most important point. This is the three-star point. This is basically the main principle and the main work of the motor is to convert electrical energy to mechanical energy, and how it does that we will just see. Okay, so we're going to watch one video which would have three examples of the most commonly seen uses of motors in your everyday life. Okay, let's go. Okay, so this is the first example. What do you see here? You see a mother and a child, and they're putting clothes into the washing machine, right? The washing machine is the first example. The second example is the ceiling fan, or the fan that everyone has in their homes. And the third example is the fridge or the refrigerator. So these are the main three examples, or which are the most common examples you can say that you see in your everyday life which uses the motor. Okay, okay, let's go forth. So applications of electric motor in our daily lives is what we just saw. First was our washing machine, then our electric ceiling fan, and then our refrigerator. So it is used as an important component in the fans, electric fans, the refrigerators, washing machines, then the mixers or the mixie that you see in your kitchen that make a lot of noise, right? And your computers and MP3 players. Okay, so now I hope you have an idea about how you are actually surrounded by electric motors even if you don't realize it. Okay, now let's go on and study about it. So the construction of an electric motor. So first of all, I'm going to tell you what all are the parts of an electric motor, and then we will see how exactly it works to convert, what did we study? Convert electrical energy to mechanical energy. Okay, so whenever we have to study any appliance or a device like an electric motor, what we first have to study is what are the different parts it has, and then we will see what role does each of those parts play. Okay, so first we'll see what all the different parts are. Okay, so first of all, you can see one of the most important parts is the magnets. So in this picture, it might look like the North Pole and the South Pole are like two different detached boxes. That is not how it is. This is actually a connected magnet. This could be a horseshoe magnet actually. Look, if I connect it like this becomes a horseshoe magnet, right? So it is actually a complete magnet only, even if in the picture it looks like it's like two detached poles, north and south pole, but that's not how it is ever. The north and south pole are always part of one big magnet. Okay, so let's read in your PPT and then I will explain each and every small part. So it says that the coil is placed between the two poles of a magnetic field such that the arm CD and arm AB and CD are perpendicular to the direction of magnetic field. Now, what coil are we talking about? Can you see here this A, B, C and D? These 4 points are actually this coil. So as I explain it to you, I will draw it side by side so that you can draw it with me and you have it clear in your head what each part is. Okay. Okay. So first I'm going to draw this coil. The coil is basically not a circular coil or a loop that we have studied like. It is a square shaped loop. Okay. That it's called a coil only. So look, here I have my this is what it looks like. This is actually, I should draw it like this because it's not in the plane, it's actually in the horizontal plane, it's not standing up. So I should draw it like your figure shows it. I should draw it a little bit like this. So does this give you an idea that it's actually placed like this, as if it's kept on a table between these two magnetic poles? Okay, now if you think about it, if this coil is kept on the table and the two magnets are kept like this, how does the magnetic field go? The magnetic field goes from the north to south outside the magnet. We know that. So isn't the direction of the coil perpendicular to the direction of the magnetic field lines? How? We will just see. Look, this is how our coil is placed and this is how our magnetic poles are placed. Right? So our coil is in this direction. Like if you consider this arm of the coil, the magnetic field line here is perpendicular to it. Similarly, the magnetic field line is also perpendicular to this arm of the coil. So this line or this arm of the coil that is parallel to the magnetic field line does not come into play. Okay, great. Let me draw this for you again. So this is your coil, right? So this is your coil and this is A, B, C and D. And this is what it means by AB and CD are perpendicular to the direction of magnetic field, just as I showed it to you right now. Okay. The arm BC is parallel to the magnetic field. Okay. The ends of the coils are connected to two halves P and Q of a split ring. Now, what is a split ring? What is a complete ring? A complete ring looks something like this. Right? This is a ring. Now a split ring is when this ring is split into two halves and it is separated like this. This is a split ring. So you can see there is this gap between the two halves of a split ring. Okay, great. Now what is done is this P and Q that you see right here. Can you see this P and Q right next to the letter D? These P and Q are the two split rings, and this cylindrical object that you see right here, this gray colored cylindrical object is called the axle. The axle doesn't play any part, but it just provides that area for rotation of the coil. You remember we had said that it has a rotating part. The coil is the part that rotates, and how we will just see. So these split rings are insulated on the inner side. What does that mean? So you came here, you came till this point. You know what the coil ABCD is. You know that there is one north pole here and one south pole here. And you know that the magnetic field lines are going like this from north to south, so that the magnetic field lines are perpendicular to the arms AB and CD, right? This much we know and we are clear about. Okay, now let's study about the split ring. So here we have an axle. An axle is nothing but just this cylindrical object which is just there to help in the rotation. Now, I said that these split rings P and Q are insulated on the inside. What does that mean? What does insulated on the inside? It means that suppose this axle is, or this cylindrical object is made out of a metal. Say it is made out of any metal, and I have a split ring which is also metallic. So when current flows through this split ring, wouldn't current also flow through this metallic object? Metals conduct electricity, right? So if there are two split rings here, if this is one split ring and this is the other split ring like this, so what would happen? From this split ring, current would flow to the other split ring. So it would actually become one full ring. The whole objective of having a split ring is that there is no conduction of electricity between these two rings. Okay, so that is why they are insulated on the inside. So if I have to show you a little clearly, what this looks like is, if this is the cylinder, which is the axle, and the split ring is like this. It goes under. Okay, the other piece of the split ring is also like this. It goes under and it attaches to the bottom part of the axle. Okay, so if this is my cylinder, if this is my long cylinder, then my split rings are like attached to it without touching each other. They're attached to the both the sides of the cylinder, which is the axle, and they're insulated on the inside. These split rings, the inside, this caving part of my hands, if my hands are the split rings, these caving parts are insulated so that no electricity flows from one split ring to another. Because if one split ring to another electricity flows, then it's completely like a ring. Then there is no point of having it split, right? So just so that that middle conducting axle or the cylindrical rod doesn't become the conduction line or like a conducting wire between the split rings, we insulate it on the inside so that no current flows from one split ring to the other. So I hope that is clear to you now. Okay, so we have one split ring here. This is P, and we have the other split ring here, which is Q. Okay, now what happens is this our coil is not actually directly attached to the split rings. Why? Because the split rings are not stationary. They can move on the axle. They are free to move. So we have these brushes. This is one brush X and this is the other brush. This brush, by brush I just mean this piece that is stationary there. It's just called a brush. Okay. So this brush is what this coil is attached to. My coil ABCD is attached to this brush. Okay, and then this conducting brush is then connected to a circuit. Great. So this is my complete setup. So I hope this is clear to you now that we have one coil ABCD which is made up of insulated copper wire. This coil is insulated copper wire. Okay. It is placed between two poles of a magnet. Here we are. I forgot to write south, north and south pole. This arm AB and CD are perpendicular to the direction of magnetic field. We have seen that. The ends of the coil, the ends, by the end I mean, look, ABCD, the end is this point. These are the end points of the coil. These end points are connected to two halves P and Q of a split ring. So they are attached to the split ring. Okay, this is not attached to the brush. This is actually attached to the split ring only. Okay, just make that correction. Okay, so why it is attached to the split ring? It is attached to the split ring because the split ring can move and the axle moves. So what happens? The coil moves with it. It is going to become a little more clear when we do its mechanism and its working. Okay, so right now you just need to know that the coil ABCD has its end connected to the split rings P and Q. These split rings are insulated on the inside so that no current flows between these two. Then these split rings in turn are connected to the brushes X and Y. So these brushes X and Y, these brushes are the brushes that the split rings are connected to. Okay, and these brushes are stationary. What does that mean? That they can't move from their places. That means these two brushes stay at one point, but the split ring can move on that cylindrical object in the middle or the axle. Okay, and these brushes are then connected to the battery, and that is how the circuit is completed. You can have a key here also. So current will flow in this direction. The current obviously flows from the positive of the battery to the negative. It goes to this brush X. From this brush X, it goes to the split ring. From the split ring, it goes into the coil like this. And it comes back to the battery like this. Okay. So this is how current flows in this setup of an electric motor. So I hope that is clear to you now. Okay. Let's see what the next slide says. So this is what I exactly explained to you right now, that the inner side of these halves, that means these halves of the split rings, are insulated and attached to an axle. What is the axle? The axle is this cylindrical object to which the split rings are attached. Okay, they are attached like this. You can just imagine if you're holding any cylindrical object like this without letting your hands touch, and you are insulating it on the inside so that there is no flow of current between the two split rings. Okay, then it says that the external conducting edges. Why did it say external conducting edges? Because the internal sides or the inside of the split ring we have insulated. So when we insulate something, something becomes an insulator. Will it conduct electricity? No, right? But the outside parts, because P and Q are actually conductors only, we have insulated the inside of it, but the outside is still conducting. So these conducting edges of P and Q touch the stationary brushes X and Y. Okay, so I hope this whole setup is clear to you now, and why X and Y are stationary, and why the split rings move, and why the coil is connected to the split rings. All of that is going to just become clear when I explain you the mechanism of the electric motor. Okay, great. So to understand how the working of the electric motor goes on, you have to remember your Fleming's left hand rule, because that is the only thing that we are going to be using to understand how an electric motor works. Okay, let's go. So this is the same setup that I showed it to you. ABCD is the coil. Second point is ABCD is connected to P and Q split rings, which are insulated on the inside. On the inside means on the side which is touching the axle or the cylindrical object, right? On the inside, so that no I, that means no current, flows from P to Q. Okay, so there is no current flowing here between P and Q. They are divided. If you can see, if you look carefully only, then you will be able to see that there is a very small gap between P and Q, but they are not connected. No current is flowing through them. So it doesn't happen like the current comes from here through X, it goes to Q and then comes back. No, this part does not conduct electricity. The current goes from X to P, which is the brush, stationary brush, to P, which is the split ring, then it goes through the coil. Okay, great. Okay, so we said that ABCD, which is insulated on the inside so that no current flows from P to Q. Okay, the third thing is that P is connected to X and Q is connected to Y. X and Y are stationary brushes. Stationary conducting brushes. Okay, they are also conductors. Now I come to the working of it. So for the working, I'm going to ask you to draw the magnetic field lines in case of this magnet. So what happens? The magnetic field lines flow from north pole to the south pole, right? So think about it like this. The magnetic field lines are going like this in this direction. And first we consider the arm AB. Now this is the explanation, this is the setup. Now we are going to do the working. One arm AB. Okay, when we are considering arm AB, I always suggested to you that if you are not able to visualize from the diagram or the picture that is given to you, just imagine that that coil is kept on the table, so that it makes it more realistic for you to imagine it. So if the coil is kept on the table and the north pole and the south pole are here, and you can see that in coil AB, the current is going from, is it going from A to B or B to A? In coil, in the arm AB of the coil, look at this direction of current. It is going like this, right? So it is going from A to B. And in arm CD, which direction is current going from? C to D or D to C? It is going like this because it's a coil, right? The current is going in a complete circular motion, right? So it goes from C to D. That is something that you have to keep in mind. Okay, so now we look at arm AB. what do we notice? We see that using Fleming's left hand rule, tell me what did each of the fingers mean? What did the index finger mean? Which direction should the index finger point in? It should point in the direction of the magnetic field. Which direction should the middle finger point in? It should point in the direction of current. And which direction should the thumb point in? It would give you the direction of force. So now here what do we know? Do we know force? No, we have to find out force. Do we know current? Yes, we know the direction of current. Do we know the direction of magnetic field lines? Yes, we know it because we know it goes from north to. Take my middle finger, I arrange it in the direction of the current. It is going like this, right? It looks in that slide that it's going slightly like tilted, but imagine it on your table. And imagine this coil is kept on your table. A, B, C and D. A, B, C, D. This circular coil is kept on your table. And in arm AB, the current is going from A to B. That means it's going away from you. And the two magnet poles are kept like this. So the magnetic field is absolutely like this. That is from west to east. So I take my middle finger. I put it along the current. I take my index finger. Where is my magnetic field pointing? Like this or like this? It is pointing from north to south. So again, do it yourself. Take up your hand, arrange your fingers in the direction of the current and magnetic field. You will get to know what the direction of force is. For me, according to me, the direction of force is coming downwards. Is it coming downwards for you too? If it's coming downwards, very good. You've applied the Fleming's left hand rule correctly. If you have not got the direction as downwards, look at the diagram again. Try to visualize it. If you want to do it according to the diagram, you can do it again. Look, if I take my middle finger and I put it in a direction a little tilted. Now I have to put my index finger also in the direction of the magnetic field. So my magnetic field is also kind of tilted like this only. Still my thumb points downwards, right? So we say, using Fleming's left hand rule, we see that force on AB is downwards, right? It is in the downward direction. Great. Now, in the arm, so in case of arm CD, now we do the same thing for the arm CD. Okay, now look at arm CD. In which direction is the current flowing? Is it flowing towards you or away from you? It is flowing towards you. Okay, so current is my middle finger. I arrange my middle finger towards me. And I know that the north to south is the magnetic field. That means the magnetic field is pointing towards the right. So my index finger should point towards the right. Okay, it is pointing towards the right. So which direction is my force in? It is in the upward direction. Great. So again I write, using Fleming's left hand rule, on CD, force is upwards. Now think about it. This is my arm AB. This is my arm CD. This is not showing the direction of current. I'm just representing my arms like this. If the force on AB is downwards and the force on CD is upwards, then what is going to happen? Isn't the coil going to rotate like this? It is, right? Now it will make more sense to you why the coil's ends were connected to the movable half rings and not to the stationary brush, because the coil is going to experience this force. So it needs to be free to move because of this force. Okay, so what happens after this is this P and Q. You can just imagine these are my half rings P and Q, and from P and Q my coil is attached to my finger like this. Just look at me for 1 second. Okay, and when the force is experienced by the arm AB in the downward direction and CD in the upward direction, this half rings rotate like this and they basically exchange places. So what happens? Look at Q here. If I draw this for you, if I draw this again, this is my P originally, right? And this is my Q originally. This is P and this is Q. What happens? And this is the arms of the coils that are attached to P and Q. So what happens, because AB, this is A, B, C and D. So because AB experiences a downward force and CD experiences an upward force, it rotates in an anti-clockwise direction. And when it rotates, it comes a 180 degree and it comes like this, such that my Q is here and my P is here. So, which was the arm attached to Q? Look at this. Which arm is attached to Q? Is AB attached to Q or is CD attached to Q? CD is attached to Q, right? So, my coil becomes like this. Sorry. So, my coil becomes like this. This is C, D and this was B, A, right? This is how my coil becomes after one time the force is experienced by the coil. Now think about it. Now, if you think about this, the first case has happened. Now, if you think about it like this, if I change the letters here to make you understand it better, would X and Y change? Would X move here and Y move there? No. Why? Because we said that X and Y are stationary. They cannot move from their places. So, can P and Q move? Yes, P and Q are movable brushes. So, what happens? After this rotation, because AB experiences a downward force and CD experiences an upward force, the coil moves like this, and because the coil ends are connected to P and Q, AB is connected to P, CD is connected to Q, so it rotates and Q comes in the place of P and P goes in the place of Q. So this looks a little bit like this. This becomes Q and this becomes P. Then which arm was attached to Q? The arm was DC. Okay, and here which arm was attached to P? Look at this. First A and then B. First point A and then B. So A and B. This D is not here. So the coil actually becomes, the shape of the coil once they experience force is C, D, C, B and A. Now what is happening is the coil looks like this. So this is my half ring. Which half ring is this? This half ring is Q because CD is attached to Q, and there is the other half ring. This is P because AB is attached to P. Now the brush here is X. The brushes X and Y can't move. So this is same brushes still. And like this they are connected to the battery. Right? Now in the second case, once they have changed their position one time, what happens now? How is the current flowing? The current is flowing like this, like this, like this. The magnet is here. This is the south and this is the north. Like this, the current is flowing. Again, now this was the working part A, right? Now you will write after one cycle. After one cycle, what does that mean? It means after P and Q have been replaced and the coil has turned once. Again, you talk about first, now you talk about arm CD first. In arm CD, what happens? Now I'm not going to write the whole sentence. Now you know you can write using Fleming's left hand rule. Now I'm just going to write here what is the direction of force. Again, apply Fleming's left hand rule. In CD, the direction of current is away from me, okay, and the direction of magnetic field is towards right. So my hand should be like this. Okay, this is current and this is magnetic field. So the force is downwards. So do you remember the last time in the first case, what was the direction of force on CD? It was upwards, right? But now it's downwards. So we can write that force is downwards. And in case of arm AB, in second case, look at arm AB. Which direction is current flowing from? It's flowing from B to A, whereas in the first case, it was flowing from A to B. So to understand what changes actually comes about in this apparatus, you have to draw it with your own hands. You have to use Fleming's left hand rule yourself, and only then would you be able to understand it properly. Only then would you be able to see it side by side that okay, the coil was ABCD first, now the coil is DCBA. Earlier current was flowing from A to B and then C to D, but now in the second case current is flowing from D to C and then B to A. If you don't make this by yourself, this would not make sense to you. Okay, now coming back to arm BA, the current is flowing towards me. Okay, and the magnetic field, is it towards the left? No, it is towards the right. So force experience this upwards. So again I write that force is upward. So can you see that the force is actually reversed? In this case, look at this. B has force downwards. Now B has force upwards. In the first case, CD has force upwards. Now CD has force downwards. So this is the reverse in the force that takes place. Now what happens? CD experiences a downward force and AB experiences an upward force. So again it turns anti-clockwise and it comes back to its original position. So are you seeing what is happening? Originally the coil turned like this. Then after that, it experiences a force that makes it turn back to its original position. So the coil, after this rotation, after the second cycle, after one cycle is completed, and after this one and these two processes are completed, the coil again comes back to the position A, B, C, D that we started with. And again, it goes back to the first step that we wrote here, where arm AB experiences a downward force, CD experiences an upward force. So what is happening? This coil is actually continuously rotating anti-clockwise. So did you see what is happening? The electrical energy from the battery is turned into mechanical energy because work is being done. There is some force that is happening. Some work is being done in turning the coil. So that is how a motor converts electrical energy to mechanical energy. Okay. Okay, so now I hope among all of these things that I have written, it is clear to you how exactly the electric motor works. Okay, so now can you think about what is the basic phenomenon that is behind the working of an electric motor? Can anyone think about it? What is the reason that this coil is rotating? It is experiencing a force. So what is the reason? The reason is actually the principle, or the reason is actually the force that is experienced by a current carrying conductor when it is placed in a magnetic field. Can you see it? ABCD is the coil or the current carrying conductor, and the magnetic field is the magnetic field between those two poles, north and south. And the coil AB experiences a force in this way that makes it turn and turn and turn again and again and keep on going like that. So the principle actually is the force experienced by a current carrying conductor placed in a magnetic field. Okay, let's move on. Now this is what a commercial electric motor looks like. That was just to tell you the functioning and the basic structure of a commercial motor. This is the commercial motor, and what are the differences in the normal motor that we studied and the commercial motor? We use an electromagnet in place of a permanent magnet. What is an electromagnet? You had studied that when you keep a magnetic material like a soft iron core inside a solenoid so that it is exposed to a very strong uniform magnetic field, that piece of material, magnetic material, actually starts behaving like a magnet, which is known as an electromagnet. Now, why is an electromagnet preferred? Can someone think about it? We have permanent magnets. Why do you need electromagnets? That is because you can't control how strong the magnetic field of a permanent magnet is, like a bar magnet. You can't change the magnetic field strength of the bar magnet. It is fixed. When the magnet is made, it is made to have a fixed magnetic field, and it is made to have a magnetic field at all times. You can't switch the magnet's field on and off in case of a bar magnet, right? If you've kept a bar magnet somewhere, at any point in the day, if you take a little stapler pin near it, it will attract the stapler pin, right? But an electromagnet, because we make an electromagnet, it is not naturally a magnet, that piece of soft iron. we make it an electromagnet so we can actually control how strong of a magnet we want to make it. If we want to make it a super strong magnet, then the solenoid that we put it inside, we would give it a very high current so that the magnetic field inside the solenoid is very strong. If we want to make a little less stronger magnet, then we would have a little less stronger magnetic field inside the solenoid, and so on. So electromagnet is preferred because we can control strength of magnetic field. And the second thing is, like I said, a bar magnet, you can't just switch off the magnetic properties of the bar magnet, right? It is always a magnet at all times. But in case of an electromagnet, it does not act like a magnet all the time because we gave it that magnetic property, so we can take it away after some time. It does not remain a magnet forever. So we can have a magnet not behave like a magnet all the time. Okay, the second thing that is different in an commercial electric motor is that the coil has many turns, which means that coil ABCD that you saw had just one single turn, right? It just went around once. But in an commercial electric motor, that coil has many number of turns. Okay. The next difference is that this coil, we said that this coil has many turns. So this coil is wound around. That means that many turns are done around a soft iron core. Okay, why is that done? Because this iron core, soft iron core, plus the coils or the turn of the coils is together called the armature. This is the technical term for it. These two together are called the armature, which enhances power of the motor. That means because at a commercial level, when you are using a commercial electric motor, you just don't want a little bit of mechanical energy to be produced. You want to power whole cities, whole apartments, whole towns, whole countries. So you want huge amounts of power to be generated, right? Huge amounts of mechanical energy to be generated. That is why we use this soft iron core on which the coil is wound. Okay, so I hope the commercial electric motor is clear to you. Okay, so now that we're clear with this, let's move on and do a few questions. Okay, so the first question says, state Fleming's left hand rule. Okay, so we know that first of all, we have to stretch our thumb, index and middle finger in a way that they are mutually perpendicular. Okay, let's write that first. Fleming's left hand rule states that if we hold our thumb, index and middle finger in a way that they are mutually perpendicular. Mutually perpendicular means that each of one has to be perpendicular to both the others, that they are mutually perpendicular to each other. Then you write the three main points. Then what does the thumb give us? The thumb gives us the direction of force on conductor, right? Conductor, you can write current carrying conductor also. Second, what does the index finger give me? Index finger gives me direction of magnetic field. The third thing, okay, what is important here that you have to write external magnetic field. Why? Who can tell me why it is very, very important to write external magnetic field? Because the current carrying conductor also generates a magnetic field. That's what we have learned in this chapter since the beginning, right? We learned that a current carrying straight wire has magnetic field like concentric circles. The loop we have learned about, right? The solenoid we have learned about. So we know that any wire that carries current gives rise to a magnetic field. But in case of Fleming's left hand rule, is the magnetic field of the current carrying conductor? No, there is always, you remember there is a horseshoe magnet placed, or there is any other kind of magnet placed in which there is a north pole and south pole, and between that current carrying conductor. You remember your activity 13.7, go back to it, your rod AB and a horseshoe magnet, where we had initially seen that there is a force experienced by the rod AB, right? So that rod AB, the magnetic field, we are not talking about the magnetic field of that current carrying rod. We are talking about the magnetic field of any other source that we have, like a horseshoe magnet. So it's an external magnetic field. That means external means that magnetic field is being supplied from outside. Okay. So index finger gives me the direction of the external magnetic field, and the middle finger gives, don't write gives me, right, gives us direction of current in conductor. Okay, great. Let's move on. So the next question says, what is the principle of an electric motor? So I told you the principle basically means what is the main logic or main phenomena behind any working of any appliance. So we know what the phenomena is. The phenomena is that whenever we place a current carrying conductor in an external magnetic field, there is some force that is experienced by it. We saw that the force experienced by AB and CD was like in a way to rotate it counterclockwise or anti-clockwise again and again and again, right? So we write that the principle is that there is, wait, you write the whole line, okay? The principle of the electric motor is, then you write, when a current carrying conductor is placed in an external, again, this is not the conductor's magnetic field that we are referring to, external magnetic field, it experiences a force. Then you can also add that the direction of this force can be determined by Fleming's left hand rule. Right? Okay, great. Let's move on. The next question says, what is the role of the split ring in an electric motor? So, to actually think and tell in the answer what the role of the split ring is, we have to go back and think what the split ring actually does. So think about it. Just think about the diagram. Just if I draw it in rough here, this was my coil. These were my magnets, the poles of the magnet, sorry. This was my axle. This was my split ring. And this was the stationary brushes. So I don't need to complete the diagram because I just need to think about, even if you don't draw the diagram here, you can just write it. I'm just trying to explain it to you better. So you saw that when the current flows through the coil and applying Fleming's left hand rule, AB experiences a downward force and CD experiences an upward force. So when is the direction of the current in the coil reversed? When this we had this P and this Q. When this Q comes in place of P and this P goes in place of Q, then what happens? This becomes Q, this becomes P, and the coil becomes D, C, B, and A, right? That is when the direction is reversed, because Q comes in contact with this brush X. Because this half ring rotated and changed its position, the direction of current in the coil reversed from A, B, C, D to D, C, B, A after reversal. So what is the split ring actually doing? If the split ring wasn't there, the split ring wouldn't rotate, and the Q wouldn't come in contact with brush X and P wouldn't come in contact with brush Y, and the current in the coil would not be reversed. So there would not be another force experienced to turn the coil again and again in the anti-clockwise direction. So actually, the role of the split ring is to reverse the direction of current in the coil. So now we can say that role of split ring is to reverse direction of current in the coil so that the coil keeps on rotating anti-clockwise. Okay, and there is additional thing for you, that this object or any object which is used to reverse the direction of current is known as a commutator. So here the split rings are the commutators in the electric motor. So I hope you understand what I'm trying to tell you here, right? Just because the force experienced by AB in the case 1 was downwards and CD was upwards, we see that the coil moves like this. And the coil moves because the split rings that it's attached to, they also move. So the X and Y are stationary brushes. Split rings are free to move across the axle. So they move and change the direction of the coil, right? So now it's DCBA. Again, CD experiences a downward force, AB experiences upward force. Again, it goes back to its original position, ABCD. The coil goes back to its original position. So, if these split rings, if the split ring Q didn't come in contact with X after the first rotation and P didn't go in contact with Y after the first rotation, then the direction of current would not be reversed and the motor would not work. So now I hope it is clear to you why we are saying that the split ring is actually responsible for reversing the direction in the coil. Okay. So students, this is it for this lecture. In the next lecture, we are going to study a super interesting phenomenon called electromagnetic induction, which we are then going to use in our next appliance that we have to study, which is the electric generator. Okay, it has a different principle, it has a different working, and we'll see what happens there also. So in this class, we studied about the electric motor, we studied about how it is set up, what are its different components and different parts. Now you should know what happens with the coil, why is the split ring there, why are the brushes stationary, what happens after the direction is reversed, why does the coil keep on rotating and not stop after one point. Why is that? Because continuously the force is being exerted because of the current in the direction using the Fleming's left hand rule. Okay, and you should know how the electric motor works completely. So make sure you have revised all of your topics, and in the next class we will study electromagnetic induction. Okay students, I hope you enjoyed this class. Thank you and take care.